Welcome back to the Wastewater Whiteboard, everybody. By popular demand, we are doing coagulation and flocculation. I put this up for a vote on the channel, and of the 26 or 27 of y'all that voted, 81% wanted this over watt break and motor horsepower math, so this is what we're doing. The first thing I want to point out is I've got a couple words up here that I realized I kind of didn't put where they should have gone. So adsorption and polymer we're going to talk about when we get down to flocculation. The first thing I want to talk about with y'all is coagulants and coagulation. What are we doing here? And by the way, this is a intermediate advanced level conversation. This type of stuff starts showing up on your California grade 3 and equivalent, so your class B, your level 3s out there. If you're a grade 1 and 2 and you're coming onto this whiteboard lesson and you're interested, please stay and watch. If your head is spinning because you're trying to pass your grade 2, don't fill your mind with this yet. Go to your grade 2 stuff and study that. Come back when you are ready to take a higher level test. Or if you're doing this for work and you need to know what this is about, stick around. This is good stuff. Okay, coagulants. What are we doing here? We are neutralizing the charge on colloidal and small particles that are stuck in suspension. What are colloids? Colloidal particles or colloids are particles that are so small we cannot see them, but they are not dissolved. These will be caught up in a total suspended solids test. Okay, colloidals and smaller suspended particles stuck in suspension. Meaning, if you have a clarifier and the settleable solids that are part of the TSS test settle out easily, 95 to 99% of the settleable solids are taken care of in the primary clarifier if it's functioning right. These are the guys that won't settle out. They'll just stay there. They move on to the next process, okay? So we use iron I shouldn't say iron. That's not always true. We use metal salts typically in a coagulant. A metal salt like a ferric chloride or an aluminum sulfate. We'll talk about those in a second. To neutralize the charge on these stable small particles. We're in essence destabilizing them on purpose, okay? And it's funny, I kind of wrote my bullet points. My lectures, not in the order I wrote my bullet points, but follow me here. We typically use positively charged coagulants because the particulate matter in drinking water and wastewater are typically negatively charged inherently. They just inherently carry a negative charge. So we're going to use positively charged coagulants to neutralize that negative charge. If you're unfamiliar with what that means, negative and a negative repel, a negative and a positive attract. Okay, opposites attract. These are magnetic forces. Okay, excuse me. So the other thing we do, not just neutralizing the charge of these smaller particles, the other thing that these coagulants will do is they will precipitate dissolved substances out of solution. This can be organic substances, organic solids, metals. It depends on what you're targeting and what you're going to use different coagulants for different things. But one of the most common, I've got it in parentheses here, one of the most common things we target in this process is phosphorus, which is a limiting nutrient. And I'm not going to get totally into this. We're mostly talking about primary treatment here, but I'll talk a little bit about tertiary treatment as well in this lecture. But I'm going to save the phosphorus thing for part 2 of nutrient removal because this is just be a little preview for y'all. And the other thing I'm going to do, you're going to see ferric chloride here. I'll talk about this in a second. Ferric chloride has so many different uses in a wastewater treatment plant, it deserves its own whiteboard lesson. If I pull the thread on that quilt, we'll be here for an hour. There's just so much you can do with ferric chloride. But know about it for your grade 3. I'll talk about that in a second. So what we're going to do is we're going to take these colloidals and these smaller suspended particles, these TSS, and these dissolved solid precipitates, and we're going to destabilize them. We're going to pull them out of solution. We're going to pull them out of suspension. Well, they're not technically out of suspension yet, but we're going to neutralize their charges so they start kind of, instead of repelling from each other because they're all negatively charged, now you've got these positively charged coagulants, and they're going to start grabbing them. They're going to start sticking together. Okay, and we create what's called pen floc, really teeny tiny floc. And what's a floc? It's like kind of it's like a chunk. Would be a good way to put it, I guess. But these chunks have charges on them, all right? And they use molecular magnetism, I guess is a good way to say it, to draw things to themselves, okay? And this is a great way that we get impurities out of the water, okay? It creates these pin floc. And if you're doing this on clearer water, like in a drinking water plant, you'll notice your semi-clear water or your decently clear water just got cloudy all of a sudden because you just pulled all this stuff you couldn't see together and now you can see it. But now it's still stuck in suspension. So what do you do now? So we've neutralized the charge and destabilized it, okay? Like I said right here, pin floc is unstable and causes cloudiness in the water. Now let's talk a little bit about coagulants, and then we're going to get on to the next step, which is flocculation. Coagulant charges can be cationic, positive, anionic, negative, or non-ionic. I'm not going to get into the science of hydrophobic and hydrophilic non-ionic polymer and coagulant and stuff. I just think let's leave that one alone. I don't think you're going to be asked about it. If you've run into non-ionic coagulants and flocculants, please put it in the comments below. Let us know about it. But you're typically going to be using a cationic polymer. The most common, I'm sorry, I said polymer. Cationic coagulant, which is typically an inorganic salt, like a ferric chloride and aluminum sulfate. I misspoke there. You're typically going to use cationic because these are negatively charged, and their most common are ferric chloride and aluminum sulfate, or alum, A-L-U-M. They're going to write like that on the test. Know that alum is aluminum sulfate. These are the most common. And like I said, they're cationic due to the negative charge of most suspended particles. Okay, one of the biggest byproducts of using ferric chloride and aluminum sulfate is ferric hydroxide and aluminum hydroxide. These are commonly formed, and these are positively charged particles. So what you're going to start finding as you coagulate these particles, these smaller guys together, is that they're going to go from a negative charge to either a neutral charge, hopefully, or maybe even slightly positive because of these hydroxides. All right? So now let's talk about flocculant. And before we do, I want to say at the very end of this, I'm going to, when I get past considerations, I'm going to share 3 real-world experiences that I've had using coagulants and flocculants to not only get colloidals out, but also precipitate arsenic out. That was pretty cool. And I'll talk about that in a sec, or at the end. The other thing I want to say is if you're getting anything out of this so far, please like, subscribe, pass to your friends. Let's help folks get certified. Now, flocculation. This is where these 2 words up here come in. Adsorption and polymer. You're going to hear polymer used a lot on your tests. They'll just bypass the word flocculant, coagulant, and all that stuff. Typically, coagulants are more inorganic salts. Polymer is going to be, most flocculants are polymers. Not all flocculants are polymers. There's a lot of different types of polymer. I think you should definitely do some research on polymers and get to know the different kinds. But yeah, not every flocculant is a polymer, but a lot of flocculants are polymers, okay? The purpose of flocculants, or flocculation, is to bridge the smaller floc to create larger, more stable floc, okay? So these are pretty unstable. They're sitting up there in suspension. They're kind of sticking together, but you know, it's enough at this point that you could potentially pass it through a filter, but they're not going to settle out. What flocculants do is they take those smaller particles, they make them larger, and they take total suspended solids that would not settle out in a clarifier and now make them big enough. The larger floc traps more particles and now denser and will settle out. So it becomes part of that 95% of settleable solids that will settle in a clarifier, okay? So why would you do this? Why? Why are we doing this in the first place? So my plant, I don't have to do it. I don't do this. So why would you? Well, if my secondary process was just fine last year, but this year a new permit was issued, and my effluent BOD went from 30 to 10, and I can't do that on my trickling filter, or I can't do that on my conventional activated sludge. I just can't seem to hit 10. Instead of going through a $30 million upgrade to your plant, you might introduce a coagulant, a flocculant before in primary treatment, before primary, and let those TSS settle out and pull some of those organics out of solution. Some soluble BOD becomes insoluble BOD and settles out. Then now it's a lighter load on your secondary process, and now you can meet your permit requirements. That is one of the many reasons you would do this, okay? We'll talk about some tertiary in a second. Bridging, also known as agglomeration or aggregation. So I said the purpose is to bridge the pin floc, make bigger floc. You will also hear this called agglomeration or aggregation, These are also anionic, negatively charged, cationic, positively charged, or non-ionic, not charged, no charge. All right. Higher level test takers, you need to know that if you're using ferric chloride or aluminum sulfate as a coagulant, the most common flocculant charge will be anionic, negatively charged, because ferric chloride and alum create these positively charged hydroxides. Okay, is that always and forever the rule? No, but that is a test question that you should be aware of, that anionic flocculants are likely used after ferric chloride, aluminum sulfate, because of the creation of ferric hydroxide and aluminum hydroxide. Okay. Now, the other thing about ferric chloride, did I already say this? I might have already said this. Sorry, this is a long lecture, so this is a sidebar. Ferric chloride has many, many, many uses. You look those up if you're getting ready to take your grade 3, because I was slapped upside the head. I was not prepared for all the many uses I'd be asked about for ferric chloride. It showed up at least 4 times on my grade 3. And I don't think it was about the same thing that I can remember. It's been years, but yeah. And it also showed up on my grade 4. Get to know ferric chloride and also know ferrous sulfate and alum. Know those. There's a lot of different chemicals, lime and all these other things. But since we're talking about it, really get to know that one pretty well. Got a lot of uses. Okay, so I'm jumping around here. All right, considerations. Oh, and so the adsorption and so polymer. Let me talk about adsorption real quick. I just kind of glossed over that. This relies on the concept of adsorption. Flocculation relies on adsorption. So let me talk about that for a second. Absorption is taking in water into a sponge. Like, that's absorbing. The sponge absorbed it. You can't see it on the outside of the sponge. It's inside the sponge now, right? Adsorption is taking it onto the exterior of itself, kind of like flocculation does. The floc is growing bigger because these charges they're bridging and they're bringing them together. This is very similar to how a water filter works in a drinking water treatment plant. Many people think a filter strains. It's just so tightly packed that only the water can pass through, and it keeps all the material. Well, a media filter, that may be how reverse osmosis works, because it's such a small pore size, but and membrane filtration. But on like a sand filter, that is not how it works. What happens actually is that you've got these charged floc coming through the filter bed, and the water passes through, and as it passes through, the floc attach to the filter media. The filter media doesn't strain it. It literally electrically grabs it using magnetic force. There's forces that we won't get into today on this, they're official, like van der Waals forces and things like that. But there's forces that grab, and then the water passes through. So when we backwash a filter, we just run the water back through the filter at a rate that we won't wash our filter media out, but at a rate fast enough to scour these floc off the filter and send it out to wherever the backwash water is going. Okay, and it just detaches from the filter media. All right. There's a whole science behind backwashing filters, flow rates, and all that stuff. So good to know. I almost totally forgot adsorption for a second time when I wrote the thing out, and then as I was teaching. Yeah. So anyway, considerations. Here's some considerations, and after considerations, I'm going to give you some real-world examples of how I've used these coagulants and flocculants. Floc shear can happen due to over-aeration and over-mixing. So over-mixing would be your paddles are moving too fast, or your flow rate's too fast through pipes if you're using a pipe scheme to mix your chemical. There's all sorts of different ways to mix chemical. Yeah, if you're these are like fluffy snowflakes. They're not like dense rocks. They're like very fluffy. And if they experience any shear force of any real magnitude, they'll just break. And then if you have floc shear, they go right back into suspension. They won't settle. You've just lost you've lost the game there. Okay. Over aeration. I mentioned that because some people do use flocculants in activated sludge aeration basins to help their floc formation. If the bacteria don't naturally do it for you, it's a totally normal thing to do to aid settling. If you're over aerating your aeration basin, you can actually shear those floc you're trying to make as well. Okay, so that's a thing. Your dosing is typically determined by jar tests or streaming current meters. Streaming current meters are pretty common in drinking water treatment plants. I don't know very much about them in wastewater plants. If you do, please comment. Love to hear about it. But the dosing is typically used in jar tests. Okay, that's a test question on your 4 or 5, right? I don't know about the 3, but advanced people know, you definitely need to know about jar tests. So in essence, what you do is you take a set of jars, typically about 500 milliliter jars, and you take identical samples, so maybe out of a composite sampler or something, or you grabbed it all at the same time in the same basin, and you put them in the jars. You got stirrers in there, and you take different doses. And what you're doing is figuring out your optimal dose. Okay, it doesn't mean the dose that gives you the best quality water, but your optimal dose. And what do I mean by that? So say you have 5 jars. Jars 1, 2, 3 are kind of whatever. Jars 4 and 5 give you similar results. Okay, maybe 5's a little better, but 4 used 60% of the chemical that 5 did. You would probably go with 4 because you don't need it to be. You're in essence overdosing if you get to 5. So that's that's the level of jar test question you're probably going to encounter, is that you're looking for the optimal dose, and they might give you some numbers. Here's your dose, and here's the quality that you came up with, and then you have to figure out what your optimal dose is. So be ready for something like that. That's very much a T4 drinking water question, but do not be surprised if you run into that on your higher level wastewater, because you're getting into reclaimed water stuff there. Okay. And then sludge conditioning may be required if the sludge has very much ferric or aluminum hydroxide present. So these hydroxide Floc, I'll call it, they inhibit microbial growth. So they've got all this organic matter trapped in it, but you send it to a digester like that, and the microbes can't get to it because the hydroxides are no bueno for those microbes. And so you're not getting volatile solids reduction. You're not getting good methane production because of these hydroxides. A little bit's not the end of the world and actually could help, but too much, you need to send it to sludge conditioning. You need to undo that, and that's a whole process. Okay, so I want to give you that's kind of coagulation and flocculation in a nutshell. If you think I missed anything, please put it in the comments below. I'd love to hear. Now I want to share 3 real-world examples with you of my experience with coagulation and flocculation. All 3 of them are drinking water treatment. Okay. I've never really had to do this in, my permits never are at that level that I'm using chemical to knock phosphorus out or anything like that. So my very first plant I worked in, it's direct filtration drinking water plant. We used an aluminum base. It wasn't alum, but it was, a distant cousin of alum as a coagulant. And we used chlorine as a coagulant aid. And we had to be careful with that because of THM formation. But we just need a little bit of chlorine. And anyway, it mixed, it neutralized those colloidals, kind of made a pin floc. It's all we needed. We didn't need huge, settlable floc in there. And we sent it right to direct filtration, right to filter beds, and it did a great job. Okay. Second experience was chemically precipitating arsenic out of solution. Okay. So that's kind of what we do a lot of with phosphorus. This is a tertiary treatment, so I'm going to give you my experience. This is exactly what we do with phosphorus, but in a drinking water setting. We don't pre-chlorinate for phosphorus, but in this case we had to because it was a certain type of arsenic that was not able to be precipitated. So we pre-chlorinate, it changes the chemistry of the arsenic, and then we hit it with ferric chloride, and that pulled it out of solution. Now it was a precipitate, and this right here, it took that dissolved solid precipitate and it created a pin floc, and then we hit it with a flocculant and it bridged those pin floc of arsenic, and then we put it through a filter, and using the power of adsorption, it stuck to the filter and whoop, clean water came out. Pretty cool. Third experience, surface water treatment plant, pulling out of a lake, and it came in, we hit it with alum. Immediately after that, not very long at all, we hit it with T-Floc, created those pin flocs, created those larger floc, and then it adsorbed, went direct filtration. We didn't even settle that out. It just adsorbed right to the filter media. So it depends on what your plant's designed for. You could use a flocculant and a coagulant, or you could use a coagulant. You could just use a flocculant. It just depends on what's going on. But I just wanted to give you some experience. These are not hard to work with. Like I said, the chemists come up with a lot of the dosing. We don't. We tweak the dosing based off what's going on. But the chemists kind of come up with those baselines, and then you can kind of, as an operator, goes from there. All right. You typically aren't reinventing the wheel. Now, if you're a chief operator, which if you're a grade 4 or 5, you are, or you're able to be one, you have a seat at the table when they're designing this stuff. I've been in a lot of meetings for my plant. We're going over reclaimed water right now. We're talking about the UV skid we're going to put in. I just read an email before I turned the camera on about, different UV skids we can put in for this treatment process we're adding to the plant. And I have a seat at the table. I need to know about this stuff, And so it's not that I'm going to be the one that comes up with the dosing scheme. It's just that I'm going to be the one that has to deal with it after everybody leaves. So anyway, with that, if you got anything out of this, please comment, like, subscribe. If you have any questions, please ask. I want to answer all questions. And if you deal with this more than I do, I am not the end-all, be-all of all knowledge in the universe. I just know a lot about it. If you've got anything to add, please put it in the comments below. And with that, I will catch you guys in the next one. Have a great day.